analysis for any refrigerant system is we take control volume across each component and we apply mass and energy balance for each component. Like that you have to apply mass and energy balance for all the components, and then you get a set of equations, then you have to supply required number of inputs and you get the output when you are getting the properties and all from your inputs. Okay. So let me explain how this is done and with suitable equations. Okay. I will just give an example. For example, if you are taking let us say the evaporator. Okay. If you are applying mass balance to the evaporator, what is the mass balance to the evaporator? Remember that here this cooling water, chilled water and all don't come into picture, okay, because we are not really considering how we are supplying heat or how we are rejecting heat. Okay. So for our analysis we are concentrating only on the refrigerant side, that means inside the system. Okay. So if you are applying mass balance for the system, you know that which is steady flow, so whatever mass is entering must go out. That means m dot 3 should be equal to m dot 4. This is the mass balance. And what is the energy balance? Since it is steady state, whatever energy is entering must leave the control volume. Okay, this is our control volume. So for example, in this case energy entering is QE. Okay, QE plus m dot 3 into H3. This should be equal to m dot 4 into H4. Okay, so this is the mass balance for evaporator and this is the energy balance for the evaporator. Similarly, you take control volume across the absorber and again you apply mass and energy balance. Similarly, you take control volume across each component and apply mass and energy balance and you arrive at a set of equations. Okay, now let me show the equations. For example, for condenser, so let us begin with condenser. Only refrigerant, pure refrigerant vapor enters into the condenser and 1 is the entry state point at the inlet and 2 is the state point at the outlet. So m dot 1 is the mass flow rate into the condenser and m dot 2 is the mass flow rate out of the condenser. Okay, so they should be equal because it's under steady state. And what is this? This is nothing but the refrigerant flow rate. Okay, because only pure refrigerant is entering into the condenser. So the mass balance is very simple. M dot 1 is equal to m dot 2 is equal to m dot. And similarly, if you apply the energy balance, remember that we are neglecting kinetic and potential energy changes. And in condenser there is no work transfer. So you have only heat transfer and fluid flow. Okay, so if you are applying that, you will find that heat rejected from the condenser QC is simply equal to mass flow rate of the refrigerant into the enthalpy difference, where H1 is the inlet enthalpy and H2 is the outlet enthalpy. Okay, so this is the energy balance for condenser. And what is the condenser pressure? Condenser pressure is nothing but the saturated pressure of pure water at condenser temperature Tc. Tc is the condenser temperature. Okay, so these are the all that we need to know about the condenser. Similarly, you apply the mass and energy balance for the expansion valve. This is the mass entering and this is the mass leaving, and this is again equal to pure refrigerant flow rate m dot. And since the expansion process is isenthalpic, there is neither heat transfer nor work transfer. Okay, so the enthalpy remains constant. So H2 is equal to H3. Same way, if you apply the energy and mass balance for evaporator, this is the mass balance, pure refrigerant enters and pure refrigerant leaves, and this is the refrigeration capacity. This is an important parameter. Refrigerant capacity is again given by mass flow rate of refrigerant into enthalpy difference across the evaporator. H4 is the exit enthalpy, H3 is the inlet enthalpy. Okay, again how do we find the evaporator pressure? Evaporator pressure is nothing but the saturated pressure of pure water at evaporator temperature TE. Okay. Now let us come to the absorber. In absorber we have both refrigerant as well as solution. Okay, so first let us apply the total mass balance. This is the total mass entering into the absorber, this is the total mass leaving the absorber. What is the mass entering into the absorber? This is the pure refrigerant mass flow rate, and this is the strong solution flow rate from the generator. Okay, this is what is entering into the absorber. What is leaving the absorber is a weak solution. Okay, so the total mass flow rate is conserved. Okay, now you can from the definition of circulation ratio, you can write m dot SS as lambda into m dot, where lambda is a circulation ratio. So if you substitute this here, you can easily show that the weak solution flow rate is nothing but 1 plus lambda into m dot. Okay, similarly you can also write an energy mass balance for the refrigerant. So mass balance for the refrigerant means whatever amount of refrigerant is entering into the system must leave the system. So what is the amount of refrigerant entering into the system? First it is entering in the form of pure vapor, that is m dot, plus the solution also consists of refrigerant. Okay, so what is the amount of refrigerant in the solution? That is nothing but your solution flow rate into the mass fraction of refrigerant in the solution. That is nothing but 1 minus zeta SS, where zeta SS is the concentration of lithium bromide. So 1 minus zeta SS is the concentration of water. Okay, so this is the amount of pure refrigerant entering into the absorber. And what is leaving? Weak solution is leaving the absorber. So what is the refrigerant in the weak solution? It is nothing but, I am sorry, there is a mistake here. This should have been 1 minus zeta Ws into m dot Ws. Okay, so this is the weak solution refrigerant in the weak solution. Okay, so from this equation you can easily show that if you combine these two equations, you can find an equation for circulation ratio in terms of the concentrations. Okay, this equation is important because once you know the concentration, you can easily find out the circulation ratio. Circulation ratio is an important parameter because the COP of the system depends upon the circulation ratio. Okay, now let us write the energy balance for the absorber. What is the energy balance? Whatever energy is entering must leave. What is the energy leaving the absorber? Energy is leaving the absorber through the cooling water, that is equal to QA. This is nothing but the absorber load, and m dot H4 plus lambda into m dot H10 is the total energy entering into the system through the refrigerant and through the strong solution. So this is the energy entering into the absorber by way of fluid flow. Okay, and what is leaving the absorber is this by way of heat transfer and this by way of fluid flow. Okay, so this is the simple expression. Now we can also write this expression in this form. So the absorber load QA can also be written as m dot is common, H4 minus H5 plus lambda into H10 minus H5. Okay, and this term H4 minus H5 is nothing but the difference in enthalpy as the refrigerant vapor at state 4 is getting converted into solution at state 5. Okay, so this accounts for the phase change of the refrigerant vapor from refrigerant from vapor to solution. Okay, and this accounts for the sensible heat transfer part. What is this thing? This is nothing but the sensible heat to be transferred as the solution at condition 10 is cooled to solution at condition 5. Okay, so you can see that this consists of two terms. Normally from the performance point of view, from the absorber size and all, this should be low. Okay, this should be low. This parameter has got to be low. Okay, because other parameters are decided by other performance related issues like your refrigeration capacity and all. Okay, so you can see that when circulation ratio is low, the heat rejected at the absorber will be low. Okay, now we can also apply mass and energy balance across the solution pump. It's very easy. Only a weak solution enters the solution pump and it leaves the solution pump. So m dot 5 is a weak solution entering into the solution pump, and m dot 6 is a weak solution leaving the solution pump. Okay, so this is the mass balance. And what is the energy balance? We assume that this is adiabatic. Okay, adiabatic means there is no heat transfer, right? Then there is only work transfer. So work transfer is nothing but if you are neglecting kinetic and potential energy changes, this is equal to mass flow rate of the solution into enthalpy rise across the pump. Enthalpy rise across the pump is H6 minus H5, and m dot Ws can be written as 1 plus lambda into m dot. So this becomes 1 plus lambda into m dot H6 minus H5. Though this equation is a correct equation, this is not very convenient to use in calculations. So we can make one simple assumption that the weak solution is incompressible. Okay, if you are assuming that it is incompressible, that means its specific volume remains constant. Then you can get this expression. How did you get this expression? You can also use expression like this, minus VdP, okay, from state 5 to 6. This we have discussed in the while presenting basic thermodynamics. So work input is integral VdP. So if V is constant here, so you can write this as this is the mass flow rate into P6 minus P5. Okay, where P6 is the exit pressure, P5 is the inlet pressure. Okay, and P6 and P5 are known to us because P6 and P5 are nothing but condenser and evaporator pressures. Okay, and you can take an approximate value for the solution specific volume because it doesn't really vary much. So you can take some average value and you can calculate what is the power input to the solution pump. The power input to the solution pump, if you remember, is negligible compared to the heat input to the system. Okay, that means in COP calculation you can really neglect the solution pump work, but still you have to calculate what is the amount of work required to the pump, because when you are designing the system you have to select the motor, and you have to select a suitable pump and the motor for the pump. Okay, that means you have to specify what is the required capacity of the motor. So for that purpose you have to know what is the work input to the pump. Okay. Now we will continue this and we apply the mass and energy balance to the solution heat exchanger. In the solution heat exchanger, two streams enter. Weak solution enters from one side and strong solution enters from the other side. Both don't get mixed, so weak solution flow rate is conserved here and strong solution flow rate is conserved here. Okay, and the QHX is the heat transferred in the heat exchanger, which is nothing but m dot into delta H for the weak solution. That should be equal to m dot into delta H for the strong solution. This is under the assumption that there are no heat losses or gains in the solution heat exchanger. Okay, so this is a simple energy balance equation for a heat exchanger. Now we can also write the mass and energy balance for the generator. This is the total mass balance. Okay, this is the total mass balance. So mass entering is nothing but your weak solution mass flow rate, m dot 7 is the weak solution mass flow rate, and what is leaving is your refrigerant mass flow rate m dot plus strong solution mass flow rate m dot SS. Okay. Similarly, you can write the energy balance equation. This is the energy supplied in the generator, and this is the energy leaving the generator, and this is this is the energy supplied to the generator, this is the energy leaving the generator, and this is the energy entering into the generator by way of fluid flow. Okay, so this is simple energy balance, and there are no work transfer here, so you don't find any work terms. This can also be written in this form, m dot into H1 minus H7 plus lambda into H8 minus H7. That means again it can be written as a sum of two terms, H1 minus H7 plus H8 minus H7. What is H1 minus H7? H7 minus H7 is nothing but the energy required to generate water vapor from a solution at state 7 to a superheated vapor at state 1. Okay, so this is the energy required for that purpose, and this second term accounts for the sensible heat transfer. This is nothing but the energy required to heat the solution from state 7 to state 8. Okay, so one is some kind of a latent heat term, the other one is a sensible heat term. For high COP, again QG should be low. So you will see that for QG to be low, again the circulation ratio should be small. Okay, so when you have small circulation ratio, you will have small QG. Again, the difference between H8 and H7 should be small as possible. And remember that H8 minus H7 are the enthalpies of strong and weak solutions. Okay. Now again you can finally you have to write the mass and energy balance for the solution expansion valve. Again, whatever mass is entering is leaving, and this is nothing but your again there is a mistake, this is m dot strong solution. Okay, and this is we are assuming that this process is isenthalpic process. Okay, so the enthalpy remains constant, there is no work transfer here, and kinetic energy changes are negligible. Finally, the COP of the system is given by refrigeration capacity divided by the input to the system. Input is in the form of heat to the generator and the solution pump work. As we have seen in the last class, this is negligible compared to this, so this is approximately equal to QE by QG. You can also define what is known as second law efficiency or exergetic efficiency as a ratio of the COP of the system divided by the maximum possible COP. If you remember, this maximum possible COP is for an ideal vapor absorption refrigerant system, and we derived an expression for this. If you remember, that is the expression is nothing but COP max is nothing but TE divided by TC minus TE into TG minus TC divided by TC. Okay, so this is the expression. If you are substituting that expression here, you get this expression. Okay. No, normally the operating temperatures, weak and strong solution concentrations, effectiveness of solution heat exchanger and the refrigeration capacity are taken as inputs, because to get the performance you have to supply certain inputs, and these are the typical inputs to any system design. And from these inputs and from the set of the equations you have to arrive at the required performance parameters. It is generally assumed that the solution at the exit of absorber and generator is at equilibrium. Okay, if you want to use the solution property tables, that means charts and tables, that what we have shown, PT concentration and enthalpy temperature concentration charts. Remember that these charts are for equilibrium conditions. Okay, so in an actual system you may not find equilibrium concentrations or equilibrium situation of equilibrium, but for calculation purposes we have to assume at some points that the solution is at equilibrium. Okay, so the standard practice is that the solution that is leaving the absorber is assumed to be at equilibrium, and similarly the solution that is leaving the generator is assumed to be at equilibrium. So what is the advantage of making these kind of assumptions? Once you make these assumptions, then you can use the equilibrium PTX and HTX charts, and you can find the required properties like required concentrations, temperatures or enthalpies. Okay, so that's why we have to make this type of assumptions. Remember that the actual situation will be slightly different from this. Okay. Now the temperature of superheated water vapor at state 1 may be assumed to be equal to the strong solution temperature T8. Remember that the water vapor that is leaving the generator is at a temperature almost close to the generator temperature. Okay, and what is the pressure inside the generator? It is same as the condenser pressure. Okay, so the vapor that is leaving the generator is at a pressure equal to the condenser pressure, but at a temperature much higher than the condenser temperature. So obviously it is in a superheated state. Okay, so typically we assume that the temperature of the vapor that is leaving the generator is equal to the temperature of the strong solution that is leaving the generator. Okay, so you have to make these kind of simple assumptions so that you can perform the calculations easily. Okay. And we also require solution heat exchanger effectiveness, and this is defined as, normally heat exchanger effectiveness is defined as, if you remember from our heat transfer discussion on heat transfer, this is defined as the actual heat transfer rate to the maximum possible heat transfer rate. Okay, the actual heat transfer rate can be written as, for example, Q actual can be written as m dot, for example, if you are writing in terms of strong solution, m dot SS into Cp of strong solution into delta T of strong solution. Okay, Q maximum is nothing but m dot Cp of strong solution into delta T max. Okay, that is what we have written here. Delta T max is T8 minus T6. Okay, and T7 minus, there is again a small mistake here. So this should have been T8 minus T9. Okay, so this is the temperature of the strong solution leaving the entering into the heat exchanger, and this is the temperature of the strong solution leaving the heat exchanger. Okay, T8 and T9 are inlet and outlet temperatures of strong solution at the heat exchanger. Okay, T8 minus T9. From the above equation, the temperature of the weak solution entering the generator can be obtained, since T6 is almost equal to T5. Okay, so this temperature is almost equal to T5, which is nothing but the inlet temperature to the solution pump. That means when you are pumping the liquid using the solution pump, its temperature remains almost constant. Okay, so you can make an assumption that the inlet temperature is same as the outlet temperature. Okay, then you can you know this. Okay, and T8 is your generator temperature. So from this you can find out what is T9. Okay, so that is the use of this particular equation. So what I have given here is typical steady state analysis of a single stage vapor absorption refrigerant system. You don't have to remember any of these equations. All that you have to do is draw the system schematic and label them and take component by component and start applying mass and energy balance for each component. Okay, and of course you have to make the simplifying assumptions that I have shown earlier, and if you do it in a systematic manner, you will have a set of equations, and you will find that you have to supply certain inputs to the problem, so that you can get the required performance parameters, such as your required mass flow rate of refrigerant, what is the pump solution pump work, what is the heat input to the generator, what is the heat rejected at the condenser, absorber, and all this information is required in the design of the actual system. Okay. Now let us look at some practical problems associated with water lithium bromide systems. The first problem is, as I have already discussed, is the crystallization.